Here we have the limit comparison test. It's actually rather similar to the direct comparison test. It's another test that allows us to take a series that we don't know about its convergence or divergence and compare it with a series that we do know. So in this case, this series right here, we want to know. And the Bn represents the series that we already know. So the simplest version of the limit comparison test that we'll be using simply says that if you compute a simple limit, basically the rate at which these terms compare with each other, and if that ratio is finite and non-zero, then basically they grow at a similar rate. If one of them's finite, then this describes the finite ratio between the infinite sums, and if one of them's infinite, well, any finite multiple of infinity we would think of as infinity. So both series will converge or both series diverge. The trick is that this limit here that compares the terms, we put the ones that we want to know on the top and we don't already know on the bottom. And if that difference is between zero, if that ratio, limits between 0 and infinity, that will be a matching convergent or matching divergent series. So let's take a look at an example where we put that to the test. So this is a series that we could also use with the direct comparison test to prove. But the nice thing about limit comparison test is that this process of choosing what we compare with, let's compare with, and what we do is we just take this and we pick a similar looking series that we happen to know if it converges or diverges. For example, I could just drop off the plus 5, 2 over n to the 1/3, n equals 1 to infinity. And never mind the constant multiple on the top, what matters is that it's a p-series. And since 1/3 is less than 1, it diverges. Less than or equal to 1, actually, is enough to show that it diverges. So we're comparing with this, but we haven't actually done the comparison. The comparison is where we take this limit up here from the limit comparison test. So I'm going to take the limit as n goes to infinity. And remember that the question, the thing that you want to know, it gets put on the top. And these terms, the ones you know about, go on the bottom. So 2 over n to the 1/3 goes on the bottom. 2 over n to the 1/5 plus 5 goes on the top. And I'm going to compute this limit. So I'm going to flip the denominator. I believe I miswrote this. It should be 1/3 plus 5. Flip the denominator. We can cancel these 2's. So I'm taking the limit as n goes to infinity. N to the 1/3 over n to the 1/3 plus 5. And a simple way to evaluate that, if it's not obvious, is to factor out n to the 1/3 on the top and bottom. That leaves me with 1 over 1 plus 5 over n to the 1/3. And as n goes to infinity, that goes to 0, giving me a 1. And the important thing is that the limit exists, and it's between 0 and infinity. All right, it can't be an infinite limit. It can't be a 0 limit. It has to be not equal to 0, and definitely not limiting to infinity. All right, once we've computed this ratio here, the limit of this ratio, we got the number between 0 and infinity. Basically what this says is that because it's the number 1, both series grow at exactly the same rate. Therefore, both series, well, either both converge or diverge. We already said that one of them diverges, though. We already knew that that one diverges. Therefore, both series diverge.